was also awarded this prestigious Sloan Research Fellowship in 2018. And his work on average length of elliptic curve is well known to all of us. So Professor Arul Shankar. Hello? Hello?
We can't hear you. I think he's speaking.
I beg your pardon, I had a technical glitch. Thank you. Thank you so very much for the invitation. It's such a great pleasure to be here. I wish I could be there in person, but next best, I'm very, very happy to be here remotely. I hope I can be heard somewhat smoothly, but please feel absolutely free to ask questions at any time. I'll monitor the chat in case anyone wants to type in a question, but I'd also love to hear questions from anyone in the room. Great. So perhaps without further ado, I'll get started. Okay. So first of all, everything I say is not everything, but like the sort of main result I'll be talking about is going to be joint work with Manjul Bhargava and Ashwin Swaminathan, and the result I'll be going to talk about is the result on the arithmetic statistics of elliptic curves. So let's get started by talking about what an elliptic curve is. So an elliptic curve. So first of all, let me say, so an elliptic curve is over a field K is a genus 1 curve cut out by an equation of the following form. So it's a genus 1 curve cut out by an equation of the form y squared equals a cubic polynomial. So I'm going to write that as x cubed plus ax plus b. Such that this cubic polynomial must have distinct roots. So the cubic polynomial, I mean, the roots don't have to be defined over the field, of course, but the roots must be distinct. So in other words, the discriminant of this cubic polynomial must be non-zero. Okay. So one thing I want to say that over R, we've probably seen examples of what elliptic curves look like, and they look something like this. And one of the amazing things about elliptic curves, so because it's a cubic, so first of all, I'll say because this is a cubic equation, if you draw any line, it's going to intersect the cubic at exactly 3 points. Okay, so if it intersects, so this you can see over R, but over any field, it's easy to check that if you intersect at 2 points in the field, then the line through them must intersect it at a 3rd point also. And if you just set P plus Q plus R to be 0, where 0 is the point at infinity. So you take all solutions. So you take all solutions to this equation, to this cubic equation. You take all solutions to the equation y squared equals x cubed plus ax plus b. You add to it 0. I'm going to call it 0. That's the point at infinity. And for every line that intersects this curve, you say that that if this line intersects the curve at the 3 points P, Q, and R, then you set P plus Q plus R equals 0. If you do these things, then E, this elliptic curve, so then the points of E form an abelian group. And it's sort of very widely studied. It has applications. I mean, there's a lot of number theory that's developed around studying elliptic curves over number fields. There's also many applications to elliptic curves in many other wonderful areas, like in cryptography, in error correcting codes, and there you study elliptic curves over finite fields. So elliptic curves are a sort of very basic mathematical object which are used quite a lot. And today we're going to talk about elliptic curves as they studied in number theory. And so we care about the points of an elliptic curve over a number field, in particular over Q. So let's see what happens over Q. So over the field of rationals, every elliptic curve is uniquely isomorphic to some EAB cut out by y squared equals x cubed plus ax plus b, such that A and B need to satisfy the following conditions to make it uniquely isomorphic, namely p to the 4 dividing A implies p to the 6 does not divide B for all primes B. So this is a really nice condition, and what it says is that if you're interested in understanding the set of all elliptic curves over Q, you can understand that by just studying pairs of integers A and B, such that p to the 4 dividing A implies p to the 6 does not divide B. Okay. Another important condition we need, if you'll remember from above, is that this equation, this cubic equation, must have non-zero roots. Sorry, this cubic equation must have distinct roots. Namely, it must have non-zero discriminant. So what does it mean for the discriminant to be non-zero? It just means 4a cubed plus 27b squared should not be 0. Okay, so now we have a set of elliptic curves, but now we also want to order them in some way. We're not happy with just a set. We want to order the set in some way, because if you order the set in some way, you can study the statistics of the set. I mean, otherwise it's just some infinite set. If we have an ordering, then we can start asking analytic questions. So let me tell you how to order these curves. We order them by height. We define the height of an elliptic curve. I wish I had different colors. There we go. So I'm going to define a height. And we will define the height of EAB. Remember, every elliptic curve is uniquely isomorphic to some EAB. This is going to be the maximum of 4a cubed and 27b squared. We would like to order the elliptic curves by discriminant. To be perfectly honest, we would like to order elliptic curves by discriminant, but it turns out to be very difficult to understand the set of elliptic curves ordered by discriminant, because the problem is that a cubed and b squared, for all we know, could get very large and the discriminant could still be very small. So to avoid anomalies like that, we just order by the height and let E denote the set of elliptic curves over Q. and let x, for a real number, positive real number x, let Ex denote the set of all elliptic curves in E that have bounded height. Okay, and now we can start asking questions about the statistics of Ex. So in particular, suppose f is some function on the set of elliptic curves, and I'll tell you some very natural things that we can set f to be later on, but suppose f is some function, then we denote the average of f to be, we are going to first, so I mean, like, what do I mean by the average of f, right? This is where we need an ordering. This is why we need to order E in some way. But because we've ordered E by height, what we will do is we will first average f over Ex. So we will take summation E in Ex, f of E, and we will take the average of this. So we divide by the size of Ex, and then we take the limit as x goes to infinity. And this is something that we can do. And if the limit exists, then we say that the average value of f exists. And so we can talk about the average value of f even over this infinite set of elliptic curves. Okay. So what kind of functions do we want to average over elliptic curves? So let me start telling you about some very interesting properties of elliptic curves over Q. So we already know that the Q points of an elliptic curve form a finite form an abelian group. And here is a beautiful theorem that's due to Mordell. And this theorem is that, so E is an elliptic curve over Q, then E of Q is this group, this abelian group that we've already spoken about. E of Q is finitely generated. So it's a finitely generated abelian groups. But what do finitely generated abelian groups look like? Finitely generated abelian groups look like T direct sum Z to the R. That's what every finitely generated abelian group looks like. So therefore, E of Q is going to be isomorphic to T, where T is some finite group, to the power of times Z to the R for some integer R. I'll call it R of E. So here, T is a finite group, finite abelian group, and R of E is called the rank of E. Okay, so Mordell's theorem buys us this much. It tells us that these groups, E of Q, look like some finite abelian group plus some number of Z's that show up. And the number of Z's that show up is called the rank of E. Now, Mazur has an amazing theorem that tells us that T has very few options. So there are in fact only 15 possibilities for T. And moreover, it's not too difficult to see using the Hilbert irreducibility theorem that the average size of T is just 1. So what that means is that 100% of elliptic curves have T as just the trivial group. Now, there are an infinite number of elliptic curves, which are still just 0%, that can have other possibilities for T. So, for example, Z mod 2Z can occur, Z mod 4Z can occur. There are infinitely many elliptic curves that don't have T trivial, but 100% of E do have T trivial. Okay, so in this limit, as we take this limit, it will turn out that very, very few, a negligible number of elliptic curves have non-trivial T. Okay, so I mean, studying T and studying sort of, what happens to the torsion, what happens to the torsion parts of elliptic curves, that's a very deep problem. But as you can see, statistically, it is not particularly difficult. Statistically, it is just true that the average size of T is just 1 because 100% of elliptic curves have T trivial. So instead, in this talk, we're going to talk about the statistics of the rank. Okay, so that's the preliminary question, which actually has, there are some deep conjectures that predict exactly how the rank should behave statistically. So here's the conjecture. It's due to Goldfeld and Katz-Sarnak. And the conjecture goes as following. So what it says is that 50% of elliptic curves have rank 0, 50% have rank 1, and the remaining 0%, which are still going to be an infinite number of elliptic curves, the remaining 0% don't mess up the average. The average is what we would expect. So the average value of the rank is exactly a half. Now I'll point out that the 0% of elliptic curves that have higher rank are themselves a very mysterious set of objects. So for example, it is not at all, it's been a topic of much discussion whether the ranks of elliptic curves over Q should be unbounded. There was a period when the consensus was no, then it shifted to yes, then it shifted to no again. And right now we believe, I'll mention this beautiful conjecture. It's due to Park, Poonen, Wood, and Voigt. And this conjecture says that the ranks of elliptic curves over Q are bounded. So it's absolutely bounded. This function that assigns to an elliptic curve to its rank doesn't go to infinity. And in fact, they're explicit about what the bound should be. The conjecture says that the ranks are bounded by 23. Actually, I've forgotten. Maybe it was 27. I'm just going to put 27 to be safe, plus big O of 1. There's, of course, a good reason for why there's a big O of 1. They're stating it simultaneously over many number fields, but this is what the conjecture is for Q. So these 0% of elliptic curves that are supposed to be extremely rare are very mysterious. It's like if you want to ask a question about is the rank bounded or not, like these are very, very difficult questions for which about which we know very little. We don't even know whether it's true or not. Like this conjecture, for example, was quite recent, and I mean, like there've been conjectures claiming the opposite direction as well. Like, so it's not, it's like this is a much harder thing to understand, like how erratic elliptic curves with high rank might behave. However, as is common in arithmetic statistics, if you're asking about something on average, then you expect things to behave very well. So you can see this conjecture of Goldfeld and Katz-Sarnak. It basically says that on the whole, elliptic curves are very well behaved. Half of them have rank 0, half of them have rank 1, and the average rank is a half.
Sir, excuse me.
Yes.
In the first conjecture of Goldfeld and Katz-Sarnak, how is the third statement different from the first and second? Like, what is the
excellent question? This is an excellent question. So it could happen, like a priori, it is possible that these 0% of, see, the 0% of elliptic curves that have rank greater than or equal to 2 are still infinite in number.
Yes.
Right?
Yes.
So the problem is that for that 0%, the ranks could just become absolutely unmanageable. Like a priori, that could happen. It could happen that, you have this extremely sparse, like one curve for every time you increase every time you like double your height or something like that.
Okay.
But that one curve has rank like 10 to the height or something like that. Absolutely. So 0% can affect, 0% of quantities in the limit can affect the average, but the conjecture says that it doesn't. And in fact, this second conjecture implies that it's certainly enough to imply the third statement given the first two. You're absolutely right. Okay. So now I'm going to talk a little bit about so what I'm going to do now is I'm going to talk a little bit about approaches to this conjecture. So first, let me tell you a very good reason to believe this conjecture. Okay, this is a reason that Maser gave, and as a result, it's called the minimalist conjecture, as I'll explain why. So suppose E is an elliptic curve. You can attach to E an L function. And we, of course, know by, Wiles's famous theorem that this L function comes from a L function of a modular form. And so, in particular, you can complete this L function to a function called lambda, which has an analytic continuation to the whole plane and satisfies the following functional equation. Now, what I'm doing here is I'm normalizing the functional equation so that the critical point is at a half. Very often it's normalized so the critical point is at 1, but I'm just renormalizing it so that the critical point is at a half. Okay. So, so E is an elliptic curve. We can attach to it an L function, and this L function can be completed to an L function lambda, and lambda satisfies this beautiful functional equation. And here, omega of E is called the root number, and it's plus or minus 1. Now it is so now here's the point. So first of all, I'll note some elementary properties. Suppose omega of E equals minus 1, then lambda E of a half must be 0 by the functional equation. Moreover, the Birch and Swinnerton-Dyer conjecture tells us that the order of vanishing of lambda is equal to the rank of E. So in particular, if we assume BSD, what that tells us is that the rank of E is even if omega of E is 1 and odd if omega of E is minus 1. In particular, we must have lots of elliptic curves where the rank is positive. It can't be that every elliptic curve has rank 0 because you have lots of elliptic curves where omega of E is minus 1. So now if you assume that elliptic curves have as few points as possible, so if you're a minimalist, then you will believe that when omega of E is 1, most often your rank is 0. And when omega of E is minus 1, most often the rank is 1. And that's one way to understand how the Goldfeld and Katz-Harnack conjectures are arrived at. Because you have this quantity omega of E. I beg your pardon? Oh, sorry. So you have this quantity omega of E, and if you assume BSD, then we know that the rank is, so we know that the rank is even half the time and odd half the time. But we also believe that elliptic curves in general have very few points, and so your rank is 0 half the time and 1 half the time. And this philosophy of minimalism actually had really helped us to sort of predict how ranks should behave. So one way of studying ranks, and I just want to mention this, one way of studying ranks is by using BSD. So the rank of E, if you assume BSD, is equal to the order of vanishing of lambda at this critical point. And so that's an approach that's been used to great effect by Broomer, Heath, Brown, and Young. And that's a sort of analytic way to study what the rank is. Instead of studying just the rank, you study the order of vanishing of this L function. Instead of that, I'm going to talk about an algebraic approach to studying the rank. So here's one way we can study the rank. You study the rank via what are called n-Selmer groups. So let n greater than or equal to be an integer. Then the n-Selmer group it's a finite group which fits. I'm not going to define what it is exactly, but I'll tell you the exact sequence it fits into. It fits into the following exact sequence. So remember, E of Q is finitely generated, and so E of Q mod n E of Q is a finite group. And this injects into the n-Selmer group. And the co-kernel is simply the n-torsion in the Tate-Shafarevich group of E. So this is the n-Selmer group. This is the Tate-Shafarevich group. So in particular, if you can prove Oh, I beg your pardon? Oh, sorry. Oh, sorry. If there are any questions, that would be great. But if not, that's totally fine also. Okay. So the point is that if we can say something about the n-Selmer group, we can say something about the rank of E, because the size of EQ mod NEQ is greater than or equal to n to the rank. And so understanding the Selmer groups helps us understand ranks. And I'll state this result, which is due to Manjul, Bhargava, and myself. And what we prove is that if n is 2, 3, 4, or 5, then the average size of the n-Selmer group is the sum of divisors of n. And as a consequence, we can prove that the average rank is less than or equal to 0.885. And we can prove that the percentage of elliptic curves with rank 0 or 1, remember this percentage should be 100, but we can prove that this percentage is at least 83.75%. So it's not quite Katz-Sarnak, we're quite a way away, but it's, you know, it's showing that the average rank is finite and that lots of elliptic curves have rank 0 or 1. Okay. So given that Selmer groups are so useful in studying rank, it actually makes sense to just study Selmer groups for themselves. So independently of these results, Poonen and Raines developed heuristics to understand how the Selmer groups should be distributed. So they develop heuristics for the distribution of the sizes of the P-Selmer groups of elliptic curves for all primes P. And because they can get the entire distribution, they can predict not only what the average of the P-Selmer group should be, but also what all the higher moments of the P-Selmer group should be. So for example, they predict that the average size of the 2-Selmer group of elliptic curves should be 3. So these are all heuristics. But this in fact is a consequence of this result. When n is equal to 2, then the average size should be the sum of divisors of n, which is 2 plus 1, which is 3. They predict, in fact, that the average size of the P-Selmer group for any prime P should be P plus 1. But they can, because they get the whole distribution in the heuristics, they can predict not only what the average sizes should be, but what the higher moments should be. So here's another example of one of the predictions. They predict that the average second moment of the two-Selma group, so the average, so I'll write this as cell E the whole squared. So the average size of the square of the size of the two-Selma group, they predict it should be 15. But I should point out that other than these results, these four results, computing the average size, the first moment for n equals 2, 3, 4, and 5, there are no other results that are currently known. And in fact, before the result that I'm going to talk about just now, no second moment has been even shown to be finite so far. So a priori, this could just be infinite. Like we don't even know that it converges, even though Poonen and Raines predict that it does exist and is in fact 15. Okay. So the purpose, so what I want to talk about is this recent result, which is joint with Manjul Bhargava, myself, and Ashwin Swaminathan. And what we prove is that the second moment, so the average size of the square of the two-Selma group is less than or equal to 15. Okay. So if there are any questions, I'd be very happy to take them now. If not, I will continue. Okay, so here's what so actually, so before delving into the proof of this result, which I'll sketch quickly in the last, which I'll explain how the proof goes in the last 15 minutes or so, but I would like to begin by giving a separate heuristic for why we should expect this average size of the square of the two-Selma group to be 15. So here's a second heuristic. So the reason I want to talk about the second heuristic is that our proof essentially makes this heuristic precise. So this heuristic is a very natural way to understand why the second moment should be 15. So we know, let's take as granted, especially because it's been proven, that the average size of the two-Selma group, not the square, but just the average size, we know it's equal to 3. Okay, and now we want to try and predict what the second moment is. Given that we know the first moment, we want to try and predict the second moment. So here's how we're going to do it. So what does it mean that the average size is 3? Well, every elliptic curve has an identity element in its Selma group. The Selma group is actually a finite group, right? So the Selma group definitely has an identity element. So it has the identity element in the two-Selma group. And on average, E has 2 non-identity elements in the two-Selma group. So every E has 1 element in its two-Selma group, namely the identity, but on average, it has 2 non-identity elements in the two-Selma group. So now, what does it mean to compute the average size of the square of the two-Selma group? Well, This is just the same as computing the average number of pairs sigma comma sigma prime, where sigma and sigma prime are both in the two-Selma group of one particular elliptic curve. That's exactly what the second moment is. Instead of just counting the number of elements in the two-Selma group, we have to count pairs of elements in the two-Selma group. So let's take case one. Let's divide up these pairs into cases. So case one, let's say sigma is the identity. Now, if sigma is the identity, how many sigma primes are there? Well, we know that because the number of sigma primes, because there's only one identity element, the number of sigma primes on average is 3. I'm going to write 3 in green because we have a contribution to the second moment of 3. Right? So if sigma is the identity, the average number of sigma primes we know is 3. Now let's look at case 2. Suppose sigma is not the identity. Now, if sigma is not the identity, there's something very special about this elliptic curve. This elliptic curve is not a generic elliptic curve. If sigma is not the identity, it implies that the two-Selma group of E, because remember, sigma is an element in the Selma group, two-Selma group of E, and sigma is not the identity, which means the two-Selma group of E is non-trivial. The two-Selma group is non-trivial. Now, the two-Selma is a two-torsion group, which could be trivial, it might be non-trivial. However, if sigma is an element, an identity element, then we know that this two-Selma group is non-trivial. And so we expect the average size of the two-Selma group over such E to be larger. And in fact, by the minimalist conjecture, by the same sort of minimalist reasoning that we did before, what it predicts is the average size of the two-Selma group over such E should be 6. Instead of 3 as an average, it should be 6. Because there should be an extra factor of Z mod 2Z for every such E. So if sigma is not the identity, there are 2 such sigmas on average. And for each such sigma, there's a contribution of 6. So we expect that the average size of the square of the two-Selma group is 3 plus 6 plus 6, which is exactly 15. And in fact, this is exactly how our proof goes. We heavily use the two-Selma group in order to study its second moment as well. We do something very, very similar to this. So let me now start explaining a little bit about the proof, about how one proves such results. So here is how the proof of the average size of the two-Selma group and the average size of the four-Selma group are computed. So let me start off by saying, by talking about how one understands these n-Selma elements. So the n-Selma group of an elliptic curve. So so it sits inside the cohomology group H1En. And this little part is going to be slightly technical, but it won't be used too much later on. But let me just say that what this means is that you can embed this two-Selmer group into the set of twists of what are called Brouwer-Savary diagrams. So twists of E inside E mapping to Pn minus 1 via the divisor system n times the identity. Okay. Now, what's a twist of E inside Pn minus 1? A twist of E inside Pn minus 1 is simply going to be a pair C embedding inside what is potentially a twist of Pn minus 1. But it turns out that to be an n-Selmer, that to sit inside the n-Selmer group and not merely inside this cohomology group, this curve E must have points everywhere locally, which means the thing it maps into has points everywhere locally as well. And by the local global principle for quadratic forms, what that implies is that C also sits inside Pn minus 1. C is also mapping to Pn minus 1. So an element of an n-Selmer group can be thought of as a genus 1 curve C, whose Jacobian is E, mapping inside along with the degree n map to Pn minus 1. And now, when n is equal to 2, we get a map from a genus 1 curve to P1, which is going to be, it's a degree 2 map, so it will be ramified at 4 points. So if you have 4 points inside P1, you can make a polynomial with those 4 points as the roots. And because we are looking at 4 points in P1, this will give, sorry, n is equal to 2, this will give a binary quartic form. And it turns out that, for example, so let me talk a little bit about binary quartic forms. So this is just, ax to the 4 plus bx cubed y plus cx squared y squared plus dxy cubed plus ey to the 4. So it's pretty nice. Just a homogeneous polynomial in 4 variables. So let me call the space of binary quartic forms to be V. Now GL2 has an action on V. So in fact, so the action on V is going to be gamma dot f of x comma y. I'll take a twisted action. It's just f of x comma y dot gamma, and then I'll divide by the determinant of gamma the whole squared. And under this normalization, it is easy to see that the center of GL2 acts trivially. So in fact, this action descends to an action of PGL2 on V. You can think of PGL2 as, so you have the algebraic group action. Now, over the complex numbers, there are exactly 2 polynomial invariants for this action, and they're denoted I and j. And I is degree 2 in the coefficients of f, while j is degree 3. And I'll state now a theorem which is really originally goes back to Birch and Smith and Dyer. And the theorem says, so I'm going to state it only, so I'm going to state it in a slightly weaker form. So assume that the discriminant of E is square free, which is not too much of a restriction, but just to make the statement simpler, I'll assume the discriminant of E is square free. Then it turns out that the two-Selmer group of E is in bijection with integer binary quartic forms, which have invariants. Which E are we taking? Let's say we're taking the EAB from before, with invariants I equals A and J equals B, quotiented out by PGL2Z. So it turns out we have a beautiful bijection of this sort. And so we can compute the average size of the two-Selmer group by counting PGL2Z orbits on integer binary quartic forms. Now, when n is equal to 4, something similar happens. We have this curve, genus 1 curve, sitting inside P3, and this is going to be an embedding, and such an embedding is always given as the intersection of two conics. So intersection of two quaternary quadratic forms. So in particular, I can represent those forms by their gram matrices. So I can represent this pair of forms as A comma B, where both A and B are symmetric 4x4 matrices. And I'll call the set of all such, I'll call the space of all such symmetric 4x4 matrices, I'll call it W. Oh, I beg your pardon. Oh, so thank you very much for this question. I only saw it until now on chat, but I will I'll answer it right after I talk. Sorry. So W comes with an action of GL4 cross GL2. It's a natural action. GL4, because these are 4x4 matrices, GL4 acts on it, and because there are two of them, A and B, GL2 acts on it. And so we can compute the four-Selmer group by studying. So we can understand the average of the four-Selmer group by counting GL4Z cross GL2Z orbits of WZ. But there's a problem when trying to compute the second moment, because as far as we know, there isn't any such similar natural space that allows us to do it, right? In the two-Selmer case, we had the space of binary quartic forms. In the four-Selmer space, we have this space for the four-Selmer group, we have the space W, but we don't have any such nice thing inside to parameterize the second moment of the two-Selmer group. So how do we understand second moments? So the way we do this is as follows. So instead, so remember, so in both the in the 2-Selmer case, we just studied PGL2Z orbits on VZ. And in the 4-Selmer case, we studied GL2Z cross GL2Z orbits of WZ, GL4Z cross GL2Z orbits on WZ. So we had to study the action of a reductive group acting on a lattice, and we had to count lattice points. Now what we do, so I have not much time left, I believe, so I'll just quickly summarize what we do for the second moment. Our proof is in 3 steps. So first, we try and we obtain a similar parameterization except with, maybe I should remove the word similar because it has one giant difference with the previous parameterization. So of pairs sigma comma sigma prime in the square of the 2-Selmer group. But the problem is that this parameterization is not in terms of a group orbit on a lattice. Instead, this parameterization is going to be in terms of a certain group. This is going to be a reductive group. Acting on not one lattice, but infinitely many nested lattices. So instead of just having one group acting on one space, this group, unfortunately, is going to have to act on an increasingly on a union of infinitely many nested lattices. So all these LAs are lattices, and they get sparser and sparser. So now in order to do the count as previous, so instead of just counting points using geometry of numbers, if you had just one lattice, you could just count points. But now because there's an increasing series of lattices, we have to use equidistribution methods to count orbits. So putting together these two pieces, namely a parameterization in terms of a union of nested lattices, and secondly, equidistribution methods in order to count these orbits, we can understand what we can prove that the 2-Selmer group of elliptic curves has second moment that's bounded by 15. So I think I'm just at time, so I'll stop now for questions.
There was already a question, so maybe you can address that one.
Absolutely. So let me start with the question that's already there. So instead of considering averages of rank of elliptic curves, isn't it natural to consider weighted average and give less importance to the strangely behaving members of E? No, that's an excellent question. So I mean, it turns out that it's okay to take averages because the strangely behaving members of E actually don't change the average. So we're in a very happy situation where even the few sort of anomalous elliptic curves with huge rank, they occur so rarely that they actually don't change the average. There are certainly great advantages to also studying the analytic approach. If you study the analytic approach, you can say a lot more about other statistical behaviors of the elliptic curves, such as zeros of the L function corresponding to the elliptic curves and so on. So yeah, it certainly makes a lot of sense to try and ignore anomalous behavior, but luckily for us, we don't even have to do that. At least conjecturally, this anomalous behavior should happen very, very rarely and not affect anything.
So is there any question in the audience? Yes, Krishna.
So the last, we just showed some heuristics in the last part of your talk. So can we generalize that heuristics for other primes? You were doing it for the two Selma group, not from that.
Absolutely. We can also, this is a really great question. This is actually a very interesting topic. So I mean, how do we make these heuristics, right? So yes, you're absolutely right. In this situation, we can in the situation of Selma groups of elliptic curves, we can generalize these heuristics to obtain higher moments at every primes. So it's not just the second moment of the two Selma group, but we can obtain arbitrary kth moments of n Selma groups. There's no problem that we can, this will generalize, and at least in the prime case where I checked, it agrees with the Poonen-Raines heuristics. Now, Poonen and Raines came up with very different heuristics. Their heuristics was, they modeled their heuristics was sort of very similar to how Cohen and Lenstra obtained their heuristics as obtaining a model. So like you take a Selma group, you model it, you input all the structure that it has already. Okay. So once you input all the algebraic structure that we know it has, you see the rest is just random. So for example, in the simplest case, the class group of a number field is just modeled as a random abelian group. You have to put the right measure on abelian group so you can pick out a random abelian group, but the measure is a very natural measure. It's just 1 by the size of the automorphism group of the abelian group. So for example, Z mod 3 cross Z mod 3 has a larger automorphism group than Z mod 9. So Z mod 9 you expect to occur more often than Z mod 3 cross. So these are very different ways of presenting heuristics. This heuristic is much simpler in some sense to compute.
So how easily does this heuristic translate into a proof for other primes, I'm asking?
So I'm afraid we haven't made any other case work. So I'm afraid so far it is only translated to this proof in this one situation. Because I mean, the heuristic gives us a great idea of how to proceed, but we still need these spaces to exist. So we very heavily use the fact that you can parameterize the two Selma group in terms of binary quartic forms. And so such parameterizations stop existing.
That is the key ingredient which you need to make the proof work, right? So the theorem of Birch and Swinton that you mentioned, right?
We need this very crucially, but we also need the existence of the 4 Selma group, because it turns out that the second moment of the 2 Selma group and the 4 Selma group have some relation to each other. So we also need, in order to obtain a parameterization, we need the parameterization of the 2 Selma group, we need the parameterization of the 4 Selma group. And we need different interpretations of elements of the 4 Selma, of this parameter space as well. So we need quite a lot of things that are unfortunately so far unique to the prime 2. So even though we have a parameterization of the 3 Selma group, we don't have a parameterization of the 9 Selma group. So we can't get that started off in the same way. But yeah, absolutely. So the heuristic is a useful way to start, but these other ingredients, I'm afraid, are missing for the price. But I should say one very big advantage of the Poonen-Range heuristic to this one is that they actually their heuristic is finer. We're just predicting what the size should be. They predict more than the size. Like for us, if we are doing the two-Selmer group, there's no difference because we're only looking at sizes. There's no difference for us between the group Z mod 2 cross Z mod 2 and the group Z mod 4, right? Because we're just looking at sizes. Sorry, it's a two-Selmer. In the two-Selmer case, Z mod 4 can never arise. So I mean, if you're understanding the four-Selmer group, for example, then you could have Z mod 2 cross Z mod 2, and you could have Z mod 4. And as far as this way of conducting heuristics is concerned, you can't distinguish between the two. But Poonen and Range will tell those apart as well. So their heuristic is fine.
I have another question. So earlier you were saying that some 100% of elliptic curves satisfy this or 50% of satisfy this. So is there an effective like can you quantify how many elliptic curves which do not satisfy these conditions? Statements.
That's an excellent question as well. So for example, let's take a fairly simple case, namely T trivial. So the arithmetic statistics of these torsion subgroups is not too complicated. So 100% of E have T trivial. So you can say how many elliptic curves have T non-trivial, right? It's 0%, but let's try and be more precise. So remember, how did we denote the average? We said, okay, we take the limit x goes to infinity of this ratio. Now, the size of Ex, it turns out, grows something like x to the 5 by 6. Okay, and you can prove, for example, that the size of elliptic curves where T has a Z mod 2 in it is actually around x to the 1 by 2.
Okay.
So x to the 1 by 2 by x to the 5 by 6 as the limit x goes to infinity is 0, absolutely. But you can be more precise. You're absolutely right. You can be more precise in this case. You can answer this finer question. How does it grow exactly? And in fact, there's a beautiful paper by Rob Harron and Andrew Snowden in which they compute such asymptotics for not just T being Z mod 2Z, but for all finite abelian groups that could occur from Mazur's theorem.
Can you please give me the reference? Like, can you say slowly?
Absolutely. So I'll tell you the authors. Maybe I'll write it here. Maybe this is a reasonable place to write it. So the authors are Harron and Snowden. I think they have a unique joint paper with just the two of them, so you should be able to find it on Google Scholar. It appeared in Krell.
Is there any further question? So any question from the online participants? So you can unmute yourself. Yeah, so it doesn't seem like, so I was actually going to ask the same question what Krishna has asked you already, but I'm sure the higher moments will be even more difficult. I mean, he was talking about other primes, but if you go for higher moments, to set all the things will be difficult. But it's slightly different, do you think? So assuming that the Shaw is finite, so can one do a similar study for Safarovich groups?
That's a beautiful question. So there are heuristics of Delaunay that actually model how just Shaw should behave, and that's a very interesting question, and it's also and there are sort of very detailed heuristics on how so we know how the Selmer group should behave, but there are heuristics that model how this entire exact sequence behaves.
Okay.
So this is a joint paper with many authors. So it's Bhargava, Poonen, Stoll, Lenstra, Rains, and Kane. I think those are all the authors, but they put together all the known heuristics. You know, like how should the Selma group behave? How should the Shaw behave? We know how the rank should behave, and put them all together to explain how this exact sequence itself should. Again, completely heuristical. As to what can be proven, just conditional on the fact that Shaw is finite. If Shaw is finite, you can. So, for example, in many of these cases, BSD is known. You know, so then you can start proving results, like, for example, the joint work of Bhargava, Skinner, and Zhang. You can put these things together and sort of prove things about how often curves are forced to satisfy BSD, for example. So one thing that we proved was, so a sort of joint result of myself and Manjul was that, sorry, I'm trying to locate the result. Here it is that the percentage of elliptic curves with rank 0 or 1 is quite large. And in fact, we can also prove that around 20% of elliptic curves must have rank 0. If we further assume that Shaw is finite, then we can also prove that a similar percentage, something like 15% of elliptic curves must have rank 1. So there are some very nice applications to assuming that Shaw is finite, both on the sort of heuristic modeling end, as well as on proving things about the existence of elliptic curves that satisfy certain things. So yeah, absolutely.
So let's thank President